The third law of the great Kepler allows us to easily calculate the exact orbital period of any distant planet. To achieve this, astronomers only need to know the mean distance of the studied celestial object from the Sun. The orbit of neighboring Mars is wider than Earth's, which is why its full year lasts nearly twice as long. Distant cosmic bodies move around the central luminary significantly slower than our native planet.
Hello. In this lecture, we're going to venture into the fascinating realm of celestial mechanics. My goal here is to show you how a fundamental law, figured out centuries ago, actually provides the mathematical architecture for our entire solar system. You'll see that with one single elegant principle, we can calculate the precise length of a year on our neighboring world, Mars. So, this is the central question I want us to tackle. It really gets to the heart of the predictive power of physics, this incredible ability to understand the cosmos not just by looking at it, but through the application of fundamental mathematical laws. And the tool we're going to use for this is Kepler's third law of planetary motion. For any object orbiting our sun, this law sets up a direct mathematical link between its orbital period, we'll call that t, and the semi-major axis of its orbit, which we call a. And by convention, to make things simple, we measure the period in Earth years and the distance in what are called astronomical units. Okay, so let's apply this law to a very well-defined problem. We are going to calculate the sidereal period of Mars. Now, that's just the scientific way of saying the length of one full Martian year as measured against the distant background stars. You know, what's so remarkable about Kepler's law is just how efficient it is. It only needs one single variable to work, and that's the semi-major axis of Mars's orbit, which we know is about 1.524 astronomical units. And since 1 AU is simply the average distance between the Earth and the Sun, this tells us right away that Mars orbits roughly 50% farther from the Sun than our own planet. All right, now that we have the semi-major axis, we can get right into the calculation. The formula itself only requires two distinct operations to solve for the orbital period, t. The process is really quite straightforward. First, we take that distance value, a, and we raise it to the third power. Then, second, we just take the square root of that result. That'll give us the period. So let's go ahead and perform these operations right now. So, for the first step, we cube the semi-major axis. That's 1.524 multiplied by itself 3 times. The result we get is approximately 3.54. Now, this number itself doesn't have an intuitive physical meaning just yet, but it's the necessary intermediate value we need for our final step. And now, for the second and final step of our calculation, we take the square root of that intermediate value, 3.54, and the result, which Kepler's law tells us is the orbital period t, is approximately 1.88. And there we have it. Our calculation gives us a result of 1.88. So what does this mean? It means one Martian year is the same as 1.88 Earth years. We've just determined the sidereal period of Mars. Now, while 1.88 Earth years is scientifically precise, it's not the most intuitive number, is it? So to help us conceptualize this, let's convert this duration into Earth days. We just multiply it by 365.25. And the result is approximately 687 days. That is the length of one complete orbit of Mars around the Sun, but expressed in a unit we can all readily understand. It really is a remarkable achievement to get this number from just a single measurement of distance. But how can we be so sure of this theoretical result? I mean, a core tenet of physics is empirical verification. You have to check your work. So we must now test our calculated value against what we can actually observe in the sky. For this, we turn to something called the Synodic period. Now, this is a different measure of time. It's the period we observe from our moving platform here on Earth, the roughly 780 days it takes for Mars to show up in the same position in our night sky relative to the Sun. So if our calculated sidereal period is correct, it should be able to predict this observed value. To verify our result, we're going to use the Synodic period equation. We just plug in our calculated sidereal period, t are 1.88 years, we do the math, and we solve for s, the Synodic period. And we get as a value of approximately 2.14 years. And when you convert that into days, it's a nearly perfect match for the observed value of 780 days. So the conclusion here is really inescapable. The calculation is confirmed. The theoretical sidereal period we came up with perfectly predicts the empirical, observed synodic period. The mathematics holds true. It works. So, what's the fundamental truth that this calculation reveals? Let's take a step back from the numbers for a moment to appreciate the broader physical principle that this result so elegantly illustrates. Let's just compare the input and the output. Mars, as we said, is only about 1.5 times farther from the Sun than Earth, and yet, its year is nearly 1.9 times longer. So you can see this is not a linear relationship. The effective distance on time is actually amplified. And this brilliantly illustrates a core principle of orbital mechanics. A planet that's farther from the Sun doesn't just have a longer path to travel, it also moves more slowly along that path. You see, gravity's influence weakens with distance, and that results in a lower orbital velocity. This is the physical reality that Kepler's third law so perfectly describes. And that brings us right back to our initial inquiry. We've seen how a law, a simple piece of mathematics, can precisely define the orbit of a distant world. It leaves us to ponder a final, and I think profound question. What other cosmic architectures, what other hidden truths of our universe lie waiting to be revealed, not through a more powerful lens, but through the pure and elegant certainty of mathematics?
Thank you, friends. Strive for understanding and become wiser. See you soon.